Welcome to the deep dive. Today, we're getting into something really fundamental, algorithms and data structures.
That's right. Core concepts for how computers actually, well, compute.
Yeah, and I know those terms might sound a bit heavy, maybe like something from a textbook you wanted to forget.
Maybe. But they're honestly everywhere. Behind pretty much every app, every website you use.
Exactly.
Yeah.
So think of this as like your quick guide to understanding how that digital world really works without getting totally lost in the weeds. Our mission today, basically unpack what these things are. Algorithms, data structures, how they fit together, and why knowing a bit about them is actually pretty useful. We're leaning on the Hello Algo resource for this.
Yeah, it's a good guide. So where should we start? Algorithms.
Let's do it. Algorithms first. So the source defines an algorithm as essentially a set of instructions, steps you follow to solve a specific problem.
Right. But not just any old set of steps. There are some key things about them. And crucially, it has to solve the problem in a finite amount of time.
Finite time, right? Can't run forever. And it's got to have specific characteristics, doesn't it?
Definitely. First up, the problem itself needs to be super clear. You need unambiguous input, what you start with, and unambiguous output, what you want to end up with.
No fuzzy goals.
Exactly.
Yeah.
And second, it needs to be, well, feasible. You have to actually be able to do it within a finite number of steps, using a reasonable amount of time, and importantly, a finite amount of computer memory.
Okay, so it has to be practical, real-world stuff.
Precisely. And the last thing is, every single step in the algorithm needs to have a definite meaning. No ambiguity. If you give it the same input under the same conditions, you should always get the exact same output. Consistency.
Okay, so like, forget computers for a sec.
Yeah.
If I'm giving directions to my place, the problem is get to my house, input, where you are now.
Yeah.
Output, my front door.
Right.
The directions turn left, go 2 blocks. It's the blue one that's the algorithm.
Well, that's the algorithm, yeah.
It's feasible, hopefully not too many steps. And if my directions are clear.
Anyone starting from the same place should end up knocking on your blue door. Yeah, perfect analogy.
Cool. So that's algorithms. What about the other piece? Data structures.
Right. So if algorithms are the instructions, data structures are about how you organize the data that those instructions work on inside the computer, obviously.
Organizing the information.
Okay. Yeah. And the source points out there are some key goals when you design these. You want to use as little memory, space as possible.
Save resources.
Exactly. And you want operations on that data, like finding something, adding something new, deleting old stuff, changing things. You want all that to be super fast.
Speed is good.
Always. And finally, the way it's organized needs to make sense logically so the algorithm can, work efficiently with it. Think of a messy desk versus a tidy one. Which one lets you find your stapler faster?
Definitely the tidy one. So it's strategic organization, not just dumping everything in a digital pile.
You got it.
And the source mentioned trade-offs. It's not always perfect.
Oh, absolutely. There are always trade-offs. Often it comes down to, speed for one kind of operation versus another, or maybe speed versus how much memory it takes up.
Okay, give me an example.
The classic one the source uses is arrays versus linked lists. Think of an array like numbered parking spots. If you know the index, you can go straight there. Super fast access.
Right.
But if you want to squeeze another car in the middle, all the cars after it have to move back one spot. That takes time, potentially a lot of time if it's a big parking lot.
Okay, I see the problem.
Now, a linked list is more like a train. Each car knows which car is next. Adding a new car or removing one, you just change the connections, the couplings between cars. Pretty easy. Doesn't disturb the whole train much.
Much easier for adding and removing.
But if you want to get to the 10th car, you kind of have to walk through the first 9 cars to get there. You can't just jump straight to car number 10 like you could with the numbered parking spot.
So slower access if you're jumping around. Makes sense. It depends on what you need to do most often.
Exactly. Need fast random access. Array might be better. Need lots of insertions and deletions. Linked list could be the way to go. It's a design choice.
Okay. And the source also compared linked lists to graphs. How does that fit?
Yeah, so linked lists are great for things in a sequence, like that train, one thing after another. Graphs are, well, they're for representing much more complex connections. Think about a social network or a map of cities and roads.
Okay, lots of connections, not just a straight line.
Right. A graph can show who's friends with whom or all the different roads connecting cities, lots of relationships. This lets you model really complex situations and solve tricky problems.
But I bet there's a trade-off.
There usually is. Graphs let you capture all this rich information, these complex connections, but storing all that, it often takes up more memory than a simpler structure, like a linked list. So again, complexity versus resource use.
Got it. So we have algorithms, the steps, and data structures, the organization. The source really hammers home that these two are, like, inseparable.
Totally intertwined. You can't really think about one without the other in practice. The data structure is the foundation. It holds the data and gives you ways to access and change it.
The foundation.
Yeah. And the algorithm is what acts on that foundation. It uses the data organized by the structure to actually solve the problem, like building a house. The data structure is the organized pile of bricks and lumber, and the algorithm is the set of instructions, the blueprint for putting it all together.
Right. So the algorithm does the work, but it needs the data structure to make the work possible, or at least efficient.
Precisely. And the choice of data structure massively impacts how well the algorithm performs. You could have the cleverest algorithm in the world, but if your data is stored terribly...
It's going to be slow and clunky.
Exactly. Slow, inefficient, uses too much memory. Choosing the right data structure for the job is absolutely critical for writing good, efficient algorithms. It's the difference between an app that feels instant and one that makes you want to throw your phone.
Okay, that makes the connection really clear. The source also had that building block analogy, which I like. Figure 1 to 5, I think.
Oh yeah, the Lego block thing. That's a good one. So imagine you just dump a pile of Lego blocks on the floor. That's your raw input data.
Just a mess of block.
Right. Now the types of blocks, their shapes, sizes, how they snap together, that's like the data structure. It defines how the pieces can be organized.
Okay, the properties of the data.
Then the instruction booklet that shows you step by step how to build the spaceship or whatever, that's your algorithm.
The steps.
And the finished Lego spaceship. That's your output data. The result, the solved problem.
That really ties it together. The blocks, data, their shape, structure, the instructions algorithm, the final model output. Visualizes it nicely.
It does. Shows how they all play a specific role.
Now, another important point raised was about programming languages. These concepts, algorithms, and data structures, they aren't tied to just one language like Python or Java.
No, not at all. And that's super important. The logic of how to solve a problem, the algorithm, and the principles of organizing data, the data structure, they're universal concepts.
So the idea exists separately from how you write it down.
Exactly. That's where the source, hello, Algo, can show examples in Python, Java, C++, A, whatever. The underlying algorithm, maybe like sorting a list. The core steps are the same. The programming language is just the specific way you express those steps to the computer.
Like writing a recipe in English versus Spanish, it's still the same cake recipe?
Perfect analogy, yes.
Okay, and one last thing on terminology. The source mentioned that sometimes people just say algorithms when they actually mean both algorithms and data structures, like on LeetCode.
Yeah, that happens a lot. It's kind of become shorthand in the field because they're so closely linked. When you talk about solving an algorithm problem, especially in places like LeetCode or interviews.
It's just assumed you'll need to think about data structures too.
Absolutely. You pretty much always have to choose an appropriate data structure to make your algorithm work efficiently. So algorithms often functions as an umbrella term that includes the necessary data structures. It's just common usage you'll run into.
Good to know. All right, let's try and pull this all together then. What have we figured out today?
Well, we've seen algorithms are these clear step-by-step instructions for solving specific problems in a finite way. They need to be feasible and unambiguous.
Right. And data structures are how we organize the data itself, aiming for efficiency saving space, speeding up operations, even though there are often trade-offs involved.
Exactly. Arrays versus linked lists versus graphs. Different structures are good for different things.
And the big takeaway is how tightly connected they are. Algorithms need data structures to work on, and the choice of data structure dramatically affects how well that algorithm performs.
Couldn't say it better. They're a team. Understanding them gives you this foundational insight into how basically all software works.
Yeah, it moves you from just, using tech to actually having a clue about what's happening under the hood. It demystifies things a bit.
Definitely empowers you.
So here's a final thought for you, the listener, to chew on. Think about some tech you use every single day. Could be a social media app, a search engine, maybe your music streaming service.
Anything complex.
Yeah. Just take a second and consider all the data it must be juggling posts, songs, user profiles, locations, whatever. And think about the steps it must be taking to give you what you want. Finding friends, recommending music, calculating a route. How might these ideas, we talked about algorithms as the precise steps, data structures as the organized storage, be working together behind the scenes to make that service fast, smooth, and useful?
It's a cool perspective, right? Seeing the invisible machinery.
Definitely something to think about next time you open your favorite app.